Morning. If you don't know my name yet, I'm Strube from Jülich, Supercomputing Center. And I will just give a slight overview about deep learning with supercomputers. Okay. So this is just links, you will have it later. This is me, obviously, a long time ago. This is Jülich. And what I would like to show is a short video to begin with about the new supercomputer that we have there. I wouldn't have expected a computer to struggle with YouTube this year, but sorry for the bad frame rate. Okay, so what I want to talk a bit is just to show how we do parallel computing related to machine learning, deep learning on a multi-GPU, multi-node system, supercomputer. Yeah, and this is just an overview. I don't have that much time here, so yeah, it's going to be a very, very bird's eye view of this. If you want the slides, this is the link. You can just scan it. Then you can make questions, and it's mobile friendly, so. Also, if something happens with this computer, I can take one of yours. Right. So what is a supercomputer? So you probably heard of a compute cluster. All of you have one cluster at the university, I guess. And a cluster is a bunch of computers connected together doing a single job. Yeah, and a supercomputer is a bigger bunch of that. Today's supercomputers, they are basically gigantic clusters with a fancy network. The network is the most important part here. It's what makes different from a normal cluster, actually. So usually when we talk about a supercomputer, we talk about login nodes, compute nodes, and the network. Yeah. So and also usually we have a shared file system, meaning that you don't need to worry where your data is stored or generated, in the sense that all nodes should have access to the same data. Well, usually we talk about number of nodes, performance, blah blah blah. Nothing special. And this is the normal vocabulary, yeah, of a supercomputer. And how to use it? In most of the institutes of the world, we do it exactly the same way we are doing since the 50s, 1950s in this case, which is batch processing. There are ways of doing interactive supercomputing, but this is usually for development and not for training a neural network or something like this. And another thing is, you are not unique, yeah? So everybody is using the machine at the same time. So you don't use the supercomputer completely most of the time. It's too big, yeah, for most of the workload. So you use part of it. And usually when I said batch, it means that you are working on a login node and you send a job to a machine. It puts in a queue, you say, oh, I want number of requests of this machine, and then it sends to the right nodes or not. Yeah, and it works more like this, or more like this. Yeah. So again, you ask for requests, it enters a queue. When the requests are available for you, they run, yeah, and then they send the results back to you. It's not like you're seeing things happening on your screen right away. This confuses people when they are doing things for the first time on a supercomputer because they expect the same that you have on your laptop, right? And so it's really this. You send a job to a batch system. Another interesting thing is that most supercomputing centers don't have node sharing, meaning that if you know that your job should take 5 minutes, it takes 5 minutes. Yeah, there is no one else, like usually is the case in university clusters, that if someone else is doing something heavy on the same node, things get slow for you. Yeah, this is important for predictability of your runs. In Jülich, for administrative reasons, we don't let people run things for more than a day. So you should save your work before runs in a day, just because this makes sure that everybody can use the machine. So again, yeah, you connect to a login node. You don't train neural networks on a login node. You should not do that because there are hundreds of people connected to the same login node. And yeah, you submit a job, enter the queue. When it means that when you have the resources that you specified, let's say I want 128 nodes with GPUs, It runs, and then it sends back the results to you via files and to a small email thing. Okay, I finished. Yeah? And what about deep learning? Deep learning is just matrix multiplication. Yeah, so, yeah. And if we remember from the school what is a matrix multiplication, if you look at the yellow and red element, it's completely independent from the green and blue element. They don't interact in any way, meaning that you can do them in parallel. They are independent. Yeah? And so that makes it very easy for GPUs to process those things, because this is what they're good at. Yeah? They're good at running the same operation in a lot of numbers at the same time. So yeah, it's what I just said. And so this is how you paint, for example, in a GPU. Yeah, you paint in parallel because each pixel is independent from the previous one. Well, and when you're doing whatever in the modern machine learning toolkits like PyTorch and things like this, this kind of parallelization you don't need to think about. It's done for free for you. So it means done. Yeah. Are we there yet? No, not yet. There's a bit more than that, which is, so yeah, if you have one GPU, yes, the job is running parallel, you don't need to do anything, you don't need to think about it anymore. But, for example, this is a tiny, bad example of a neural network. If it fits in one GPU, good. But usually, if you're already on a supercomputer, it doesn't fit on a GPU. Yeah? So it's when things start to get interesting. It's when you have to start thinking about what you're running there. So for example, one of the first things that people do is something called data parallel. Data parallel means that the same operations are done in different parts of the data because they're independent. Yeah, so in this example, you have the same neural network running on different GPUs with different parts of your training data. Yeah, and then, for example, like this, we call it batches. Yeah, you probably know better than I do. And then you do an average of them, and then go to the next step of the thing. This is data parallel. It's the simplest thing ever. There are other things that you can look at the slide later. It doesn't matter because we don't use it. Usually those things are done when you have a slow network or smaller machines. So just for you to have the names when you check the slides later. This is, for example, if you have a very distributed network, there are people doing trainings of big neural networks over the internet, so then those things matter. In a supercomputer which is big enough as ours, it's completely irrelevant. Yeah, so we don't need it. So yeah, that's it for data parallel. You use a different data for each GPU, you keep doing the things, do the averaging of the weights of your training, and go to the next one. Well, almost, yeah. There are more levels of that. One thing is that you can do the same, but via multinode. Multinode means that you have complete nodes with their own GPUs, and then you average over the network. Yeah. This is when the network of a supercomputer gets important, because this is a lot of communication, and if you have a slow network here, you delay everybody. But before we go further, usually this is good enough. Yeah, for most cases, using data parallel tends to fulfill the needs of most of the training workloads that we have. If you need more than this, you probably know better than I do already. So, but we are not there yet. Yeah, there's a bit more. There's something called model parallel. Model parallel is when the model is too big to fit in a single GPU. Yeah. So what you do is that each GPU will hold parts of a model, like layers or something like this. And then you keep moving data from one GPU to the next. For example, here, if with my excellent animation capabilities, you do like this, the data is moving around, yeah, and then it does a back propagation and comes back. So this is obvious that there is a problem here, yeah? What is it? Eli, pardon, I don't know.
Idling.
Huh?
Idling.
Yeah. So you see that when you're processing data in one GPU, the others are not doing anything. You're wasting 75% of the time on this example here. Yeah, and so it's absurd. Yeah, I mean, there are ways. So would be like if you have each GPU in a line here, you see that there is this empty area around. So it's really a waste of time. So what you can do with this is you can pipeline, meaning you start doing things like this. Yeah, you still have to interrupt it to do the back propagation. But yeah, well, this is just a simplification of that. But actually, you make the data smaller first, so you have more things. But what happens is more or less like this: you have more, you increase the usage, but there are parts that you still have to wait. There is no escape from that. There is no running around it. We're not there yet. There's a bit more, which is when you do model parallel in multi-node, meaning you do the same thing as before, but on a multi-node level. It's just another abstraction on top of it. Yeah. Actually, we can do more than that. We can train neural networks on multi-nodes also, and you can pipeline among nodes. But then again, this is a case that is most probable. The only thing that you're doing this is on large language models. Other neural networks are not that big. Most of the neural networks don't get to this level of complexity that you need that. So again, data parallel is when you split the data over multiple GPUs and they run the whole model, and you do a gradient averaging. And then multi-node is the same, but over multiple nodes. Model parallel is when you split the model. Yeah. So those are the nomenclatures of distributing a job on a supercomputer. And yeah. So are we there yet? Yeah. Usually I would force everybody to do a demo here, but we don't have time for that today. And so let's say if I show the smallest deep learning model that I can here, and I show how to do it multi-node. So this, I managed to fit a code that trains a neural network of cats and dogs on like 10 lines of code. So what I do is bring the data, do a data loader, and I train a neural network. This is the code that does the whole thing. Yeah, I mean, you have seen this. Yeah, load data, put it somewhere, do the fitting, and there you go. So this runs in a single GPU. You copy and paste this thing, it will run. Yeah, if you have the imports and everything correct. And then so this in our current supercomputer called Jules Booster, it takes 5 minutes. If you run it without GPUs, it takes like 12 hours. And then here, this is the parallel code. Basically what changed is that the first part is that I make sure that only one of the nodes and only one of the CPUs unpack the data, otherwise I will download the data on all of them the same. And here I say just use it distributed, and there you go. So it's given for free for you. You don't need to do anything other than that. Yeah. And then when I run them on the same machine, just changing those parameters, it changes the time from 5 minutes to 1 minute something. Yeah. If you look at it, it's actually faster than 4 times because we have 4 GPUs in a node in Jülich. But because we use also multi-threading, when loading the data, it gets faster than like, what is the name of that? No, hyperscaling. Yeah. Okay, so if you look here at the loss, it's a bit worse. Yeah. The training gets a bit worse, but because it's so much faster, it's good. Yeah, you just train a bit longer and you're good. So yeah, it's more than 4 times faster in this case because the library also uses multiple CPUs and multi-threading and so on to do the data loading. And also the I/O is parallel, so that helps a lot. So as I said before, data parallel is usually good enough. If you learn this, you can run your stuff on a supercomputer way better than you can run on a laptop or on Google Colab or whatever you're using. Yeah, this is just an introduction, of course. Yeah, I cannot do that in 20 minutes. And for example, things that you have to take care of on a distributed machine like this is I/O. I/O is a much bigger problem than when you have a laptop with an SSD and so What else? And then multi-node. To change the same code to multi-node, you just change the name of nodes on a submission script and you're good. That's it. The thing takes care of it for itself. So here, this is the same thing but running on multi-node. I put 2 nodes just to see the difference. Instead of 11 seconds, it's running on 5 seconds. But then on the end, the final time of the thing is almost the same as 1 minute something. And what's the case here? 8 seconds, sorry. It's not much faster because turns out that this demo is too small to fit on the machine. It's a toy demo, yeah. And it takes like 4 gigabytes, and I put it in 2 nodes, which has 300 gigabytes of GPU memory. So it makes no sense. Yeah, I can put this as fast as I can. It will not do better than that. And so this is a too small example to give in a supercomputer, but I think it's didactic enough for a screen. And yeah, so to exercise a whole thing on the GPU, you need a bigger model, obviously. Yeah. So that's it. And if you need more than that, we give courses on training extremely large models in Jülich. We can give you a link later of the courses that we offer there. And yeah, we have like a number of courses every year on different things. Okay, that's it. You said until 10 I needed to leave. I'm leaving. Yeah, thank you. We have 5 minutes for questions. Here's just the links of where I stole the names of the things. Questions?
First thing.
Right, so I'm taking over from Alex. I'm a colleague just from the office next door. Rocco, Sedona, by the way, is my name, and my presentation will be, I'd say, a rather short connection between what Alex was saying generally on our systems and the topic of today, which is TerraMind and more broadly foundation models for EO. Yeah, it's working. So I'll start very briefly on scaling loads and why they matter, and also try to understand whether HPC can actually be beneficial for GFMs and for you all, or not. What has happened in the last decade at this point? So more than 10 years, with the first models, deep learning models. Then the parallel training, then larger data sets. So what we have observed, well, what you can observe, is that over time the size of these models in terms of the parameter count has increased drastically. Basically, yeah, if you look at the scale, it's a really impressive scale, and now we're talking about hundreds of, we're in the scale of the billions of parameters, so it's really impressive how this has happened. Will this last? Will this hold also next? That's something, of course, we don't know, in the sense that there will be probably a limit to that scale, and there will be other technologies that will come at handy. But still, this has already happened, so this is something that is here already and is impressive. But so what happened? Why did it happen? Well, of course, larger models were made possible by the increased availability of data. Sure, that is true also in our domain, not only in language, where they have large corpora of words. But mainly, well, of course, without compute, so without HPC, without high-performance devices, this would have not been possible at all, of course. So, as I was saying, scaling laws. So, are they relevant? Well, I wouldn't look at all these numbers here, or all these coefficients. These are not really important. People have been fighting over those for 5 years now, probably. But what is important here is the fact that there are ways to understand how a model might perform or will perform when scaled. And this holds true for a very high order of magnitude, which is across 7, something like that. So it means that you can predict quite well, given that you have some points for inference, and to fit these curves, how you could possibly scale the models. And this is very important because otherwise you wouldn't just scale the models for the sake of just burning resources. So what you would observe from these plots is that there are three ways, let's say three components to having lower test loss. So one is spending more compute, so burning more GPU hours, simply put. The other is increasing the dataset size, and of course the parameters count, so the model size. How these relate? Well, again, this is a matter of coefficients and these curves. It doesn't really matter here, but it's important to know that there are tools to do that can help and for practical reasons. That was for language. Is this also true for vision? Well, of course, in recent years, the models are somewhat based on the same backbones also in vision. Of course, I mean, they are vision transformers, and they are, in the end, adaptations of standard transformers, no? And yes, what happens is that this is true. So these laws, these scaling laws, apply also in vision. So is this relevant for us? Well, I argue that yes, it is. So I want to do not to this, to the next, because again, in the last 5 to 7 years, of course, a bit slower than in other domains, but this shift towards foundation models, towards larger models, more resources, more compute, has happened also in our domain, in EO. So in 2008, in 2019, they started with larger data sets, larger prepared curated data sets. Then, of course, pre-training, training in parallel on clusters. Then more data sets and more larger models. Then 2023, I believe, Prithvi EO, the first version by Johannes, who is also here in the room. Again, another important thing arose, which is the fact that we have to, of course, also validate, benchmarks, to understand when these models actually help and how much it costs to run them, so to deploy them, to pre-train them, and so on. And then we're going ahead, so there's even more to come. Of course, multimodality, and here again, TerraMind, and the reason why we're here today, basically. But what is important is that, again, this shift toward more compute, bigger data sets, is taking place also for us. This is something that is affecting already the EO community. And HPC then, is it needed? Well, I hope that by now I have convinced that yes, it is needed. It is needed for sure in the first phase, so for pre-training, because that's where massive data sets are used in self-supervised learning. That's where these techniques that Alexandre was talking about, so data parallelism, and, well, in our case, not model yet, but who knows, sooner or later it might happen too. But that is where we really need resources, where we need to spend computing time. We need to go through a lot of iterations on a very large data volume. This is done with, again, tools that are available and relatively easy to use, like PyTorch DDP, but others, of course, exist. Then the second and third stage, do we need HPC there? Well, yeah, we can use it, depending on the workload, of course. Not all downstream tasks are the same, clearly. Might be that some are more demanding, some are less, but the trend there is to, of course, use techniques like parameter-efficient tuning, adapters like LoRa, and then you can sort of make the fine-tuning lighter weight and possibly, hopefully, deploy at inference where the cost for that operation is usually much lower even than simply fine-tuning. So is HPC needed there? So at inference? Well, it depends. So if it is just you doing your small task, I don't know, flood prediction or something, well, maybe you can do it also locally or on a local cluster without burning too many resources, true. But then sometimes you might want to maybe deploy a service to the broader public. And then HPC could help, especially with this long time trend of convergence in a way between cloud and HPC, so kind of high performance cloud or something like that is already happening. So I would say that yes, of course, pre-training there is where we need a lot of GPUs, but then it's not that in the later stages we actually don't need HPC, it can help. So that's my message here. Now, I was mentioning already that in the last couple of years, with the emergence of models, of geofoundation models in our domain, also it became clear that benchmarking is important. And by benchmarking, I don't mean simply accuracy. I don't mean simply running on a bunch of downstream tasks, classification, regression, or whatever. I really mean that we need to have a sort of holistic approach to provide the community with some insights on when, in which cases to use these large models, because of course one might think that they might cost more in deployment. So of course there have been many activities, some also by us, but the point is that, again, it's very important to understand when these models can actually help and why. So here I have an example from PRIV.io. So this is an example that I kind of adapted from a table that Eli, so another person who is here today from JSC, prepared some time ago, and I kind of rendered it into a plot instead of a table to show visually what's going on. So if you look at what's going on, the dashed line is basically the supervised, so our benchmark, versus different versions of PRIV. And what's going on at inference is that if you look at the beginning of on the left side, at the left side of the plot, you'd see that this PRIV model, the geofoundation model, is performing a bit better, 3 points better, when we are fine-tuning on the whole data set. But what happens when we move to a more data-scarce region, a more data-scarce regime? What happens is that you see that PRIV, in this case, but in general, foundation models would perform, let's say, the decrease in performance in accuracy is slower. So basically it's performing better in a data scarcity regime, which is very important. It means that we can give some models to users and they perform better than if they had to train from scratch their own model. So that is something very, very relevant, I'd say, and a case that is true for many applications where users don't have I don't know, millions of samples available, let's say. That's something very relevant, so that we still are able to maintain a better, to achieve better accuracy than in training from scratch. Right, I also adapted another plot from a very, very recent paper by Pedram Gamisi and others which is also related to benchmarking in a way. And it's the other component. So the previous slide was about accuracy, but now the other component is computing cost, how much energy we're using, what about CO2 emissions. This is also important when deploying. And actually, what happens is that, okay, this plot doesn't consider, of course, pre-training. So pre-training is not included here. But if you just consider fine-tuning and inference, cost is, of course, quite similar to models pre-trained from scratch. what it means, so, but with much better accuracy compared to them. So what it means is that actually, if people are going to use these models, actually, it's not so the energy that we use in pre-training it makes sense to have spent that, because we obtain some gain, and in the end, when actual users use it, deploy, they are not really spending much more. Of course, this is still true, that there are some other complex aspects. Memory footprint is not there, so there is much more to that. But what I want to say is that these models are actually useful, so it's not that we're doing it just for fun, okay? So, again, as I was saying, it was a very short presentation connecting the two sides of things, a generalistic view on HPC, and the tutorial on TerraMind that is to come now. But my message is that the machines that you've seen yesterday, you visited at CESGA, the ARS at JSC, that is a very important component in this general environment, which is made up of different components. So, of course, pre-training, there we are needed, kind of, but also we can help when it comes to fine-tuning and inference, especially at scale, like on the new machine, Jarvis is called, right, Alex? Jarvis is the machine. Yeah, good. So some trends as we've seen, benchmarking, always to be sure that we are providing something useful, something that has an edge over the previous previous state of the art. With that, again, I hope I've convinced you of the importance of our role. As Alexandre was saying, we have many courses at JSC too on scalability, scaling laws too, but also tools to scale. So I really encourage you to look into that if you feel like you would like to embark into this sort of journey. And for the happiness and joy of Alvaro, I corrected also the exclamation mark in Galician, so this is now right? Yeah, it's not double. Good, that's it. Good. Johannes, I believe it's your time.
Cool. First of all, thanks a lot for having me here today. I'm Johannes, I'm a research scientist with IBM Research in the Zurich lab. We mainly work on deep learning to better understand Earth's surface in terms of Earth observation, but also in terms of weather modeling. So everything that happens between top of atmosphere and surface level is something we're interested in. And one of the recent models that we've been building in a project that was together with the ESA pilot and also the Jülich supercomputing center is called TerraMind. And first of all, I thought I'd start with a video that is very just to really encourage you, I think it's cool that we are now in a phase that we do a lot of open science and people like you can interact with the models, tell us where the models perform well, but also tell us where the model breaks. So we are very interested in getting feedback by the community, and participating in those summer schools for us is a great way to gather feedback. So everything that we will do today over the session will be something that you cannot only explore today, but also over the next couple of days. You will keep the AWS instance open so that you can continue to work with the model, maybe port in some data by yourself, test it in cases where you're interested in, okay? I first wanted to do a little Turing test. I gathered an optical tile. We are somewhere, okay, we cannot see that, but this on the right is Santiago de Compostela. This is like coastal area, and I was trying to then use TerraMind to generate a couple of artificial sensor images for that region. So I would be interested whether you can identify them, okay? So first of all, let's have a look on this image. Do you think this is like a acquisition, like a satellite image, or do you think that is generated artificially? Who thinks this is generated artificially? Who thinks this is an actual sensor image? Cool. Okay. I would have hoped for 50-50 then the Turing test would be really fast, but this is actually generated by TerraMind, which is kind of cool, right? Because you see, it was an optical tile and there was no real notion about altitudes, but in the generation you can pretty clearly see that TerraMind has a pretty decent understanding of there's this river valley, and if it generates artificial data, then it kind of understands about the topography of the area, which is not something that's super trivial. I will quickly jump over a couple of those because I have so many. This is another radar image that's also generated by TerraMind, and the interesting thing is this is called Sentinel-1 RTC. For people of you who are not familiar with what that is, RTC stands for it's a terrain-corrected product. So that means this is what TerraMind thinks about this area in terms of a radar image, just like before, but abstracting all of the topography away. So you can see that TerraMind kind of understands, like, from an optical image, it can generate a radar image that includes topography, but it can also generate a radar image that corrects for topography. And then we can also do stuff like ask it for the vegetation, like where it thinks to find more vegetation, where there's less vegetation. So obviously, least vegetation is where there's water bodies. There's also not too much vegetation in Santiago de Compostela itself, but then in the regions around it, there's more vegetation. We can do the same thing for land use and for digital elevation. Also, this, like all of that, was artificially generated. We didn't have to do the Turing test for all of them, but also this is like completely generated by TerraMind. What I found interesting is in the upper right of this, you see that there's still the river valley, but in the optical tile it was pretty difficult to see that. So I was kind of happy to see that TerraMind was working there as well. Okay, so with that you already know that TerraMind is able to understand cross modalities, and it can translate between those. It can generate one from the other. In the case before, we just leverage optical input to generate the other modalities. We can also go from any other modality to any of the remaining ones. So we can, for example, start with a radar image and generate optical and so on. Before we do like the hands-on session in the second block, I quickly wanted to introduce to you how this works, because otherwise probably it doesn't make too much sense for you to work with the model. I will just cover this slide and then we will go over the results of the model so you have kind of an understanding of how the model works, and then I guess we can take it from there. So first of all, the modalities that we're using on the left side, those are optical images, radar images. We also include digital elevation, vegetation data, land use, and then data like coordinates and also image captions. And then what's important to understand is that during pre-training, the only task of the model is to translate between modalities. So we show TerraMind optical images, and TerraMind has to generate, for example, radar images from that, or digital elevation images, and so on. And to be able to do that, we have to do something that we call tokenization, which is the middle part here. So that means that every image patch, like every 16 by 16 patch in an image, is translated to an integer representation. It's just a single number. And then, let's say the upper left of the optical would be translated to to integer 5, and we would have in another modality for the same area the integer 7. Then TerraMind would try to learn the correlation between those two modalities based on the integer representation, which boils down to a much simpler problem than doing everything on a pixel level, because TerraMind then effectively has to classify hidden tokens. So TerraMind would say like, oh, every time I see integer 7 in one of the modalities, I see integer 4 in the other modalities, and based on classifying those hidden tokens, TerraMind learns the correlation between the different modalities. You also see that we are inputting pixel level information, and you might question why we do that and whether we have to do that. And the short answer is we don't have to do that. The longer answer is it's more convenient for people to use if they can input images and don't have to transfer the images to token first and then use our model. That's one part of the answer. And the other part of the answer is if you have pixel level information and you have token level information for the same area and for the same images, then you already have something like a classification, right? Because you already know that, like, every time you see a forest in one of the pixel representations, you see integer 7 in the token, for example. And every time you see a river, you see token value 25. So by doing that, TerraMind not only is able to do cross-modal learning, but also within the same modalities. So within optical data, for example, TerraMind is able to classify different patches into different classes, and this is helpful to end up with a well-structured embedding space, which is the ultimate goal of most of the deep learning models. The pre-trained dataset is pretty large. It's globally distributed across 9 modalities. We will open source that in the next couple of weeks. So if you really want to bother the Jülich people with training on an HPC, download that dataset and run it over their clusters. We also did that, and it was a lot of fun. But we also needed a lot of support, so feel free to reach out for those sessions that were offered. Cool. On a slightly more technical level, what does tokenization mean? So what is a token effectively? A token is, as I said, an integer representation for an area and an image. So people typically process image data for computer vision in general in patches, right? So vision transformers operate on patch level. So a patch is a 16 by 16 pixel representation in the image. So let's say the upper left corner of the image. Now we want to have a single integer representation for that area. And the way we do that is effectively we have another model that just learns to encode that data. In our case, it's a vision transformer itself. And then you end up with an embedding space, right? And this embedding space can be further quantized. Quantization is a process where you go from a embedding space representation to this single discrete information that we want to end up with. So the way it effectively works is this encoder learns to project the pixel level data into a hypercube. And in that hypercube, you have different corners, and based on where this specific patch would sit, so let's say it's this red one here, you would just look for the nearest corner. And that nearest corner, you would assign an integer value to, say 7. And then you would say the upper left of that patch has the integer representation 7. And this is the token you end up with. So what you should take out of that is that tokenization is not something that you can do without deep learning. Tokenization is something where a model learns to think about which areas in images are similar to each other, and it tries to bring those areas to the same tokens that we then leverage as our pre-training targets. So that also means that this has to work really well, because if this is not working, then correlation learning doesn't make any sense anymore. So we spend a lot of time optimizing this, and you probably, yeah.
How is best the relation, best the distance between the red point and the different corners is based on clustering?
In a sense, it's kind of similar to that. The way you would measure it is effectively it's an end-to-end training. So if you have the token representation, say a 7, you would then task the model to go from the 7 to the patch again. And this is what's happening on the right side with the diffusion decoder. So the diffusion decoder just sees a single integer representation, and out of that has to generate the maximum likelihood pixel distribution of what that looks like, which is an incredibly difficult task, right? So that also means that our tokenizers are not designed to be the best in reconstruction. That's not their goal. The goal is that the reconstruction works so well that we can learn end to end so that the tokens are consistent in terms of their classification behavior. And actually, this brings up a really good point. overall, this tokenization process is a huge compression. So you would go from a 16 by 16 representation, and typically in Earth observation you have a lot of channels that we call bands, right? So it's like 16 by 16 by 12, and you have floating point values for that. If you compress that information in a single integer value for a Sentinel-2, that's a compression factor of around 3000x. So by doing that, you end up with hopefully a pretty consistent representation of your data, but it's still kind of a huge compression. That means that it's not designed to be reconstructed. It's designed to be the pre-training target for TerraMind. After we did all that for all of the modalities, which took us 3 months and a lot of painful learnings, we had the tokens ready, we had pixel level input ready, and what we do in the TerraMind pre-training is we then sample from all of this data. We sample input tokens, and we also sample target tokens, which are other tokens in those images. And then we task TerraMind to first embed the input tokens in the representation. Then have mask tokens for the decoder for the areas that we're interested in to generate. And then TerraMind has to predict those tokens for the areas we're interested in. So in that case, for land use, it would be those 3 rectangles. And we can compute a cross-entropy loss on that. This is really key. Computing a loss in such a complex setup is super difficult and really painful. And if we can boil it down to a classification problem that we can solve with cross-entropy as a loss, this is much more stable than if you would do it on a pixel level. So if you want to do multimodal learning, a general advice is try to not do it in pixel space. The way we do it here is we transform everything in token space, so it's already, in a sense, in an embedded representation. And then learning between modalities with that is much easier. Cool. We already saw the left side of this image. We didn't see the right side, the downstream applications. People typically use our models to do fine-tuning, which makes a lot of sense. You want to know whether your model works well in downstream applications. So this is something we have been interested in the past. Now we have 2 new bits, and one of them is particularly interesting. The first bit was what we've started with. It's multimodal generation. That's cool, but it doesn't give you something super meaningful besides like showing it in a PowerPoint slide and asking people, do you think it's generated or not, right? The question is, can you use that data for your benefit? Like, can you generate data that actually is so good that you can use it for deep learning models, for example? And this is what we try with thinking in modalities, which is the lower right bit in this slide. Effectively, thinking in modalities is like chain of thought and language. Chain of thought and language means, I mean, you all use ChatGPT, right? So you see when the model is reasoning, it generates intermediate representations, intermediate steps. So before blurring out an answer, it would like think about what it wants to tell you. And that costs additional compute. With thinking in modalities, we do something pretty similar. We tell the model, if you have to solve a specific task, say you have to segment floods, and you have optical data for that, then maybe you first want to generate radar data from that optical data and use both of those data sets as your input to do the flood segmentation. And actually, we can show that TerraMind can self-generate data that then benefits itself to be better in those downstream applications, which is a really cool finding and kind of not super trivial to me. We can talk about that later as well if you want. Cool. Talking about how those bits work, any-to-any generation. For any-to-any generation, effectively the idea is you embed all the patches from one modality, and then you have mask tokens for the other modality that you want to generate, which means we can, let's say, in the old world it would have been a reconstruction. We can reconstruct one modality from the other based on no information for that modality that we actually want to generate, right? In the past, if you would have done MAE pre-training, like mask auto-encoding, you would always need a little bit of information from your image, right? And by doing those cross-model generations, we can mitigate that. We can also chain that, which is something that I found kind of cool. So say we have a couple of inputs that we leverage in TerraMind, and then we predict tokens in that case for digital elevation. Then we can anyway, then we can additionally input those predicted tokens to the model again to condition the probability distribution so that TerraMind will not generate inconsistent results across modalities. Say in the beginning I was only using optical data for this region here, right, to generate the other ones. Now if I then generate, for example, radar data, and next digital elevation data and next LULC data, I want that those are consistent. So I want to make sure that across the different modalities, they confirm with each other. And by inputting the predicted tokens to TerraMind during the generation for the next modality, we can make sure that we have a condition probability distribution that actually makes sure that the model is not like generating a river here and next time it generates a mountain in the same area and next time it generates a sea in that area. Cool. I want to spend a bit more time to talk about thinking in modalities because it's kind of a key concept which I think is not only specific to Earth observation. I guess many people of you are interested in remote sensing, otherwise you wouldn't be sitting here, but think about it as an equivalent to what chain of thought is in language to computer vision. So in computer vision, we cannot do something like chain of thought, but if we are in a multimodal setup and we can generate one modality from the other, we can actually generate tokens for the model in a way that is like intermediate steps. And I just wanted to highlight that here. We already had that example, right? Say you want to map water bodies. The way we did it with standard fine-tuning was we would use TerraMind as an encoder, we would freeze that, we would put a decoder on top, and we would try to tune it for segmentation. Now what we can do with thinking modalities is we tell TerraMind to first generate another modality, in that case it's LULC land use, right? In land use you already have water bodies. So TerraMind already gets a primer on where to find water bodies in the image by self-generating that content. And it leverages those two representations during fine-tuning as an input to then come up with the final result. The good thing for you is, and the bad thing for us was, we implemented everything in TerraTorch so that this is completely wrapped for you. So besides that, this takes like 20–30% more compute because we have to generate that additional data. You will not really see it during fine-tuning. You will not have the pain of like first generating and then inputting. Everything is already fully automated. So we will see that later in the hands-on session. But I found that really cool because effectively you can now decide whether you want to do standard fine-tuning or thinking in modalities fine-tuning. And if you already have a couple of runs with the standard fine-tuning and you know your configuration well, you can switch to thinking in modalities and see whether it improves your performance. That brings me to performance. We already heard a bit about it. We didn't benchmark the model ourselves. We let ESA benchmark the model on a community standard benchmark, and that's called Pangea Bench. Pangea Bench was designed with the intention to show people that foundation models in the first generation didn't work better than UNets. So UNets, I mean, they're task specific, right? They are like designed for the specific application you want in the sense that you use the UNet architecture, you apply to your problem, and all weights are unfrozen, and they are either randomly initialized or from ImageNet initialized, but every parameter is trainable. For foundation models, the general promise is you freeze your encoder, you just have to plug in a very light decoder, and then you're better. And what the Pangea people showed was that this was not the case for many tasks in Earth observation. So we wanted them to benchmark TerraMind and do that comparison again. And what they found was really cool. This animation is never working. I'm doing this presentation for the 10th time now, and it was never working. Anyway, it's a bit difficult to see, but TerraMind, it's the blue lines, okay, the dotted blue line and the normal blue line. And TerraMind on average is doing 8% better than the second best geospatial foundation model, and 4% better than task-specific units that are fully trained end-to-end for downstream application. I will skip over a couple of those in the interest of time. But I mean, we get better if we use multimodal inputs, stuff like this. That's good. I wanted to cover that to give you an idea of how much thinking in modalities can benefit your downstream application. Generally, don't expect that it completely reinvents the wheel. It will not like give you 20% of improvement, right? That would be a bit absurd because it's self-generating information and it cannot make up information that's so good that your task will be like completely solved. But if you, for example, flood mapping, if your performance in terms of mean intersectional union was like around 89.7%, we make it 91%, so it's like a 2% improvement roughly. And similar for crop mapping. So in all of our experiments, we saw that thinking in modalities helped segmentation tasks. And typically the range was in like 2 to 4% improvement. All right. Who knows about future classification? Okay, a couple of people. So effectively, I mean, the idea is pretty simple, right? You freeze your encoder, you would get an embedding, and in that embedding space, you would do a kind of a classification. You can do prototypical neural networks, you can do nearest neighbor. And in order to understand whether the embedding space of TerraMind is really working well, we did that and compared it to other models. We actually also benchmarked it to our own models that didn't perform so well, like the other two, like Privy models. And those are 10% worse. And I want to come back to what I said originally when I was talking about having pixel level input and token level input. This is now where this pays off. So if you have pixel level input and token level input from the same modality, what the model learns during pre-training when generating one from the other is a classification, right? So the model already in pre-training learns to classify something even though we don't have labels. And this makes the embedding space much better structured. And for downstream application, this really helps. Cool. Finally, a note on neural compression. We have a new benchmark that was associated to a challenge at CTPR, and we were trying to understand how we can compress Earth observation data. Earth observation data is typically like quite heavy, right? Downloading all that for model training or for inference is pretty painful. So currently we are working on understanding whether we can compress all that data in the data centers before we ship it to people, and then people can use it for their downstream application without a loss in accuracy. Say one of you wants to do flood segmentation or water body mapping or wildfire segmentation or whatever it is, you would not download the actual satellite image, but a compressed version of the embedding that is ideally completely identical to what a frozen encoder would give you, right? So then you would only have to train the lightweight decoder on your end, and you wouldn't have the high download cost. This is what we're aiming for. And funnily enough, I mean, we didn't really wanted to do that, but TerraMind does perform really well on that, given that TerraMind learns compression that is pretty significant during pre-training. So it outperforms other models like factorized prior models or hyper-prior models, and it also outperforms other like foundation model architectures like Dino by me. Okay, we don't want to cover that. I mean, we are IEM, so we are also doing a couple of demos for people that are not as hands-on as you are. So we have a couple of videos on that, how we use it for different areas in the world. It's something that we call IEM Geospatial Studio. The general idea is that it's a bit like Google Earth, but you can visualize your model's inference results. And also for TerraMind, you can also visualize the generations, which is kind of fun to play with, but it's not what we want to focus on today, so let's get that. What's important to me is what I said in the beginning, we want to get feedback. So the main reason why I'm here today is it's cool to see very interested people working with our models, but B, I also want to get feedback. So if you play around with the models and you feel like something is not super usable or something is not working really well, I'm especially interested in that feedback because that helps us to continuously improve over the models. I would say with the initial foundation model that we built, Prithvi, the first version, it was maybe like GPT-1, TerraMind is maybe GPT-2, so we still have a lot of things that we want to improve over time to get to a ChatGPT-like model. All right, so everything is open source under a license that you can more or less do everything you want with it. Second, everything is integrated in TerraTorch, which is our foundation model toolkit. And it's super simple to use. Essentially, you import TerraTorch and you specify which model you want to use, whether it's with thinking modalities or without. And then you do something like model.forward, and this will train. You can even, like, if you're even lazier than that, you can just specify one config, and we have tons of configs in the GitHub repo for TerraTorch. And you can take that as an inspiration, adapt it to your use case, and then run TerraTorch fit to use that. And finally, if people need money for their summer vacation, we have something like a hackathon that will be every second month until the end of the year, where the winning team wins 1,000 euros. So it's the same story. It's cool if you can use TerraMind to fine-tune for your downstream application, but I'm more interested in seeing where you cannot use TerraMind. So ideally, let me give you one example. I had 2 students from ETH that were looking into understanding whether they can use TerraMind to generate artificial digital elevation maps for glacier in the Alps. Now, you have to understand that TerraMind is pre-trained on data from the entire globe, and it's very unlikely that it sees data in high altitude environments generally, right? It's the long tail of the distribution. So what they saw when they were generating DEM data for the Alps was that TerraMind was never predicting something above 1,621 meters, because TerraMind was just lazy and reserved 1 token in the entire distribution for that. So when they wanted to get structurally nice results, they subtracted 2,000 meters from the entire thing, so that like a peak that would be 3,000 meters in altitude was only 1,000 meters in altitude. And semantically what TerraMind did was correct, but it was not working in the sense that you could actually use it to better understand whether the Jülich glacier is melting very fast or just normal fast. So this is the kind of things that we're interested in. If you find out where the model breaks and can pinpoint it, this is really cool and something that benefits, I guess, all of us as a community. So this is like the general goal. We want to get feedback from the community because in a sense we also build those models for the community. Cool. Yeah, that's it. I guess we have a couple of minutes for questions if you have any.